Okay. As usual, my usual question, do you see the slides? Do you hear me? Everything okay? Yes?
Okay.
Good. Okay, so we've been dealing in the past lecture or two with electron-phonon interaction. And today I would like to review a little bit what we did, also because, and I apologize for that, there are several little considerations that I should have emphasized, and actually I neglected them completely in a past lecture. So I will talk more about electron-phonon interactions in general, the full theoretical approach, see a little bit, just give a teaser on how today we're dealing with calculating electron-phonon matrix elements using density functional theory, something which has come up recently in the past 10 years, 10, 15 years. Then we'll go to simpler models. I will show explicitly the calculation of some scattering rates for non-polar interactions between electrons and acoustic phonons. We'll move to the polar interaction, so the so-called Froelich interaction. I will show some examples going from dielectric breakdown to interactions of electrons with screened longitudinal optical phonons in polar materials. So some examples of this type, interfacial excitations. And then I will talk a little bit about superconductivity. I tried to learn something about quantum computing because that's where it's one of the most interesting current applications of superconductivity, except of course for the search for room temperature superconductors. And that's what we're going to do today. So the first part, the first lecture, the first hour and whatever and a half will be on electron-phonon interaction. Then we'll talk about superconductivity. It may take me a little less than the usual time. Okay, so let me remind you what we're dealing with. As we discussed last time, we've been dealing so far in calculating band structures and in second quantization with phonons, with a system which is considering electrons and phonons fully decoupled, except for screening effects, perhaps. And now we want to deal with a system which instead sees the interaction between the electrons and excitations that can be either triggered by the electrons themselves or thermal excitations. Interaction between electrons and distortion of the lattice, so phonons. We saw that they can be categorized into two main groups, non-polar interactions. I mean, everything is Coulombic eventually, ultimately, but non-polar means that we're dealing with phonons, acoustic or optical, and the electrons feel the perturbation that the presence of these phonons view as strain caused to the band structure of the system. So an electron which is moving around sees the bottom of the conduction band move up and down, depending on the type of strain that we have. So whether we're dealing with transverse or longitudinal acoustic or optical phonons. So this is an interaction which is not mediated by an electric field, so it's a short-range interaction. And so we expect that this interaction will have a strength that grows with the momentum which is exchanged between the electrons and the phonon. On the contrary, there are also long-range interaction, and these happen in materials which are clearly ionic, polar, in which optical phonons generate a dipole field, and it is this interaction between the electrons and the long-range dipole field that causes the interaction that we'll discuss later on, the Froelich interaction. There can be also a polar interaction between electrons and acoustic phonons. We're going to ignore it. It's in materials which are piezoelectric. So also polar materials, but acoustic phonons are involved. In this case, the interaction is a long-range interaction. So typically we'll have a dependence on some inverse power of Q, depending on the dimensionality of what we're dealing with. And here, at least some references of the pioneering papers in which this we'll discuss. We'll discuss again the Bardeen and Shockley deformation potential theorem, so to speak. I will mention the Harrison extension of this theorem to optical phonons that interact in a non-polar way with electrons in a crystal, and then we'll talk about Ehrlich interactions. Now, last time I gave a general overview of what we're dealing with here. Remind you that we saw that the electron, sorry, the electron Hamiltonian can be written in this form, in second quantized form. This is essentially Schrödinger equation when you look at the Euler-Lagrange equation or the Hamilton equation that you derive from this. This is the kinetic energy of the electrons. This is the interactions of the electrons with the potential of the ions, the lattice potential. Up to last lectures, we consider this as fixed, with the ions frozen at their equilibrium positions. Similarly, for phonons, we didn't consider the interaction with electrons, and if you remember, we reformulated the Hamiltonian of the phonons that already, when you write it down, has a term, has a form that reminds us of harmonic oscillators with a square of the momenta and the square of the coordinates, and we reformulated it by using the symmetry of the crystal to a problem that deals with only the ions in a unit cell. And then we quantized our phonons, and we had expressions which have a similar form for electrons and phonons. That's the usual thing that we find for all free particles in second quantizations, a collection of harmonic oscillators, and each harmonic oscillator is labeled by the band or polarization and wave vector or momentum of the particles. And when we excite one harmonic oscillator, we interpret it as having a particle now present with that particular momentum and polarization or band index in the system. Okay, so the electron-phonon interaction implies that we have to deal with this particular problem, electrons, but now the potential of the lattice is perturbed by the fact that the ions move away from their equilibrium positions because they're associated with the propagation of a phonon. So the idea is to use perturbation theory and expand the potential, the lattice potential, away from its equilibrium position. And here you may interpret this big R, which is the position of the ion in cell L and ion gamma. Again, gamma runs only over the numbers of atoms that we have in a unit cell. You may add a little zero here, saying this is the equilibrium position. We calculate the change of the potential of the system caused by the presence of a phonon that displaces each ion by this quantity. We express these derivatives at equilibrium, and then we multiply by the displacement which is caused by a phonon. In principle, this may be viewed as a functional derivative. And as we will see, for example, today with density functional theory, what we do is we calculate the total energy of the system. Then we calculate either by using perturbation theory within density functional theory, or by using approximate methods like displacing each ion away from its equilibrium position along the 3 Cartesian coordinates by a small amount, and calculate the total energy. And this total energy will change because we've moved an ion, and this change will imply that the potential caused by a single ion will move because electrons also respond to this motion. So it's not a strictly rigid shift of the ionic potential, although that's an approximation that I made last time without emphasizing it. So in principle, we have to calculate this quantity. So it's interesting to proceed in a way that the way that I did the last time, and I want to emphasize a few things about this. So what we're going to do is expand this as a power series, in a leading order only on the displacement of the ion from their equilibrium position. I remind you that in second quantization, we had an expression for this displacement caused by a phonon. If you remember, I emphasized many times that this is actually the strength of the interaction, and that is fixed by the canonical commutation rules of the phonons. And the expression was given by some normalization conditions, and then we had expressed this in terms of a canonical coordinate that we use to second quantize it. This is the polarization of the phonons. This is the displacement of the canonical coordinates expressed in displacement. And we did a little bit of algebra, and eventually told you that we can write this expression in this form. This is again the harmonic approximation in which we're expanding the potential up to the leading order in displacement. We can go to higher orders, and this is important for phonon-phonon interactions that require these anharmonic terms, which is important, for example, for thermal conductivity. But here we'll stop at the leading order in this case. The only material in which I think that two phonon interactions are important, two phonon processes are important, or multiphonons in general, which require higher order terms. One is graphene with the modes which oscillate out of the plane of graphene. First order terms or leading order terms are forbidden by symmetry, and then only two phonon processes are important. And then there is the issue, for example, of the degradation of the silicon-silicon dioxide interface, in which hydrogen atoms which are bound to the silicon ions at the interface these bonds, the silicon-hydrogen bonds, may be broken by electrons via multiphonon processes. It's an ongoing problem and it's extremely complicated. I don't think there is a solution yet. Now, I want to stress something that I didn't stress last time. In principle, these Fourier coefficients now will be different from those that we can use, for example, from empirical pseudopotentials to calculate the band structure, because this implies a distortion of the electrons, the valence electrons themselves, and all the exchange and correlation functional terms that are associated with that. So we will consider just in the following a rigid shift, which is the rigid ion approximation or rigid pseudo-ion approximation, in which we assume that the pseudopotential moves rigidly with the electrons. It captures the main components. Of course, you're leaving out some terms. So again, as I'll show you in the next slide, one can use DFT to calculate this term. As I said, we can proceed and do our calculations. This is the same expression that I had before. And you recognize that this is a term that we discussed last time. I'll show it again in the next slide, in which we can interpret the interaction as some messy interaction strength, which is given by this coefficient, plus times this coefficient, some overlap integral. This is again the same factor that I think I called script capital I, which represents the fact that the initial and final states of an electron in a crystal are not simply plane waves, but you also have to deal with the fact that they're block functions. So there will be these periodic components of the block functions, and you have to see how much they overlap between the final and the initial states. And then there are these terms which tell you that this process describes an electron, presence of an electron with a wave vector k. I ignore spin and band index here for simplicity. We are destroying that electron, converting it into electron with another new momentum, and this momentum, clearly momentum conservation, will emerge from this integral by emitting or absorbing a photon. And in DFT, now, just to give you a teaser of what we can do now, historically, for many years, this was an issue, and actually we'll go back in a few slides to what was the original idea that Shortly-Dean had of associating this change of energy, which was not amenable to any analytic or numerical calculations in the 50s, how to correlate this quantity with something that can be measured in a lab, so that we can predict or explain the electronic transport of a crystal in terms of some quantity which is not dependent on transport, which is, after all, what the predictive power of our theory should do. So it was not possible to calculate. In the past few years, density functional theory has enjoyed major improvements due to algorithms, due to the theory itself. Of course, the speed up of the hardware, which is probably the main component, so computers which are getting faster and faster. And now we can try and actually calculate this change, delta V. Here I call it delta U. The little hat, if you want, is optional. It means that I'm dealing with second quantized quantities, so these are operators on our Fock space of phonons and electrons. What we can do is actually calculate this change of energy by an explicit calculation, in which what we do is we move the electrons, the ions, each ion in cell L, because of the periodicity, typically we only deal with one cell when we look at a cell in DFT. We move an ion gamma by a given amount in each directions, or according to the polarization vectors that we find for the phonons, a particular phonon, a particular branch, whatever. We move an ion either way. We calculate the total energy of the system, and we see how much this total energy has changed with respect to the original initial condition in which the ions were at thermal equilibrium. Essentially, what we're going to get is the forces acting on the ions, but also the change on the total potential of the system. And this will account for both the change of the Hartree part. We move an ion, the electrons move with the ion. In the adiabatic approximation, they follow it instantaneously, and this will cause a different charge distribution, which is not the equilibrium charge distribution anymore. Of course, from this charge distribution, we get a new potential, which is the Hartree component. In addition, we change the exchange energy, and we can change the correlation energy. We can use various programs. There are so many DFT packages available nowadays. One package that actually offers now there's more than one, how could I call it, a post-processing package from which you can calculate electron phonon matrix element, is Quantum Espresso. I show here that actually the Quantum Espresso people themselves, between Trieste and Lausanne, have written this code called EPW, which stands for Electron Phonon Wannier. The Wannier is a convenient calculation method to reformulate the wave functions in terms of localized orbitals, a little bit like tight binding does, in order to speed up the calculations. And you can actually run Quantum Espresso. You can calculate the phonon dispersions and then call this code, and it will give you matrix elements for the electron-phonon interaction. One can do it also using VASP and this program PhonoPy, which is a Python script that calculates the phonon dispersions and polarization vectors. VASP does not offer any of these extensions or post-processing tools that are available for Quantum Espresso, but you can use, for example, the small displacement method. You move an ion 1 along the X, Y, and Z directions by a small amount. You move ion 2, then you essentially take the dot product of those forces with the displacement due to a phonon, which you can get out of the polarization vector from the portion of the program that gives you the phonon spectrum and eigenvectors. And then you can calculate matrix element the same way by integrating over the initial and final wave functions, the block functions. Unperturbed, typically, that's to the leading order. That's what it would do if you were using VASP. There are more complicated versions of density functional perturbation theory, in which, depending on the order in which you want to perform the calculations, you may actually go to the second order corrections, and then you will need the first order perturbed wave functions in this matrix element. There is a variety of algorithms that you can use. And again, there are calculations also, programs, Perturbo from Caltech and Berkeley, GW, of course, from UC Berkeley, that actually use a better method. They start from DFT, but they go beyond the DFT by using what's called the GW method. I will not talk about it, but it's a method which is not based on density function, it's based on green functions. And it's usually more accurate, extremely more expensive from a computational point of view. So there is a bunch of codes that are available today to get the electron phonon interactions and the matrix elements. And essentially the calculations involve going beyond the exchange and correlation functionals, for example, considering the Hartree component, which is the major component. You can just look at a change of the charge density that you have obtained, assuming the presence of a particular phonon or branch eta, transverse, longitudinal, acoustic, and optical. Then look at a Poisson-Green's function and get the potential, and this will give you the perturbation that you have. You add a little eta here, as I did in this particular case, telling that you have the presence of one particular phonon. This is already integrated over all phonon wave vector, but you can get a spectral decomposition and see each phonon momentum Q what is its contribution to the matrix element. So these are calculations that I wouldn't say they're totally routine, but there are more and more publications today that deal with this. I will have probably, if I'll have the time, in one of the future lectures, I will show you little drawbacks. It's amazing that density functional theory now has connected to the transport community as they have, and it's amazing that actually results are extremely consistent with whatever the transport community people have devised over the past decades. But as the American says goes, close but not cigar. We're not quite there yet. There are some issues. You cannot just say I got it from DFT and therefore it is the truth. There are several cases in which, depending on what flavor of density functional theory you use, implying what particular form of the exchange and correlation functionals you use, more concerning is the fact that depending on the pseudo potentials that you use, you get different results. If you want the in simple terms, to say it in brutal terms, density functional theory is not accurate at the level, at the KT level, that we need for transport in some cases. Nevertheless, it's impressive that we can use this, and clearly it gives us a good, I could say, baseline and trends that we can trust. Quantitatively, there is a little bit of a discussion to them. Now, one thing that I want to go back now to what we were doing before. So go back to our expressions, which is this rather messy expression. Last time we simplified it eventually in this form, which emphasized, that's the same sketch that I showed last time. It emphasizes what this expression means. We have a particular coupling constant, or coupling is not necessarily a constant, but it's a coupling which we usually represent with a little dot that we call a vertex. And then we have, in addition, this overlap integral between the block functions, which would become 1 if we were dealing with free electrons. And then we have these annihilation and creation operators, whose interpretation can be represented by this little sketch. As I told you before, we have an electron. We require that we have an electron with momentum k, and we destroy. We replace it with an electron with momentum k plus q, and the missing momentum q goes, or is absorbed, or is going to a phonon which is either emitted or absorbed. And this is the typical expression that we will use in the following. The particular form of this expression that requires this coupling, I apologize if I call it coupling constant occasionally, it depends on everything, but that's the standard terminology, can be written this way. And these coefficients, these Fourier coefficients, the potential, we'll keep them as fixed, the same that we used to calculate the band structure, for example, in what we call the rigid pseudo-Yohann approximation. But in principle, they might be different if we account for the changes of also the additional non-local terms of the potential, such as exchange and correlation. Now, I want to spend a little bit of time, which I should have done last time, drawing some conclusion for this form. I remind you, this is the polarization vectors, which is the unit displacement. It tells me in which direction the ion gamma in each unit cell moves when it is affected by a phonal branch eta and wave vector q. These will be the usual vectors of the reciprocal lattice, and we see that we dot this polarization vector with this quantity. This is the usual prefactor, which is expressing the displacement of an ion due to the presence of the phonon. Again, the usual scale factor that comes from the canonical commutation rules. Okay, one thing that we should notice is that, look at this sum. This is the same expression that I have here. I have copied it here. Consider the simple case of a crystal in which we have two identical ions in each unit cell, such as silicon, germanium, carbon in its diamond form, and so on. The argument I give here is more general, but this is easy to see. Now, split this sum in such a way that you perform the sum over the g vectors, lumping in each term the pair of g vector g and minus g. this particular crystal's cubic symmetry. So for every G, another wave vector of the reciprocal lattice will be just the same G with a coordinates with an opposite sign, so the minus G. And look at the sum over gamma now extends from 1 to 2, the 2 ions in each unit cell. Now the interesting thing is that if we look at acoustic phonons, the polarization vectors in the limit in which Q goes to 0 will be equal. At Q equals 0, they're exactly equal. They begin to differ a little bit when Q moves away from 0. But they tend to, in the limit in which Q goes to 0, they're exactly the same. Okay? I put the little wiggle here saying that in the limit in which we're dealing with small Q vectors. Now what happens that the Q terms, if we add over the 1 and 2, they just add up. In the limit in Q equals 0, this will be just a factor of 2 for the two displacements. The G terms, if you look at the sum of the G and the minus G, will cancel because the sum of these two polarization vectors is positive, the same sign, so you're left with the change of sign in G. So you're left in the limit in which Q equals 0 for acoustic phonons just with a term which is proportional to Q. On the contrary, if you look at optical phonons, now in the same limit, the displacement of ion 1 will be opposite to the displacement of ion 2. That's the definition of an optical phonon, if you wish. The two ions in a unit cell moving out of phase in opposite direction. So now we have exactly the opposite. The term which is proportional to Q cancels out when we sum over the two vectors. And the G terms that now we're canceling because of the opposite sign, now instead they add because we had a minus sign in the polarization vectors. So essentially we end up with a sum over the G, which is not depending on Q anymore. So the idea is that the interaction with acoustic phonons is such that at long wavelength, so at small q, disappears, vanishes. Instead, for optical phonons, we approach a constant. This should not come as a surprise, because physically we can understand what happens. A long wavelength acoustic phonon, in the limit in which this wavelength goes to 0, amounts just to a translation, a rigid translation of the lattice. The change of the total energy of the system is 0 in this particular limit. And so there's no interaction with electrons. On the contrary, for optical phonons, so to speak, we have a uniform translation of a sublattice of the ions 1 with respect to the ions 2. So it's like having a uniform strain occurring on throughout the lattice. And then clearly this will correspond to a non-zero change of the energy of the system. And this perturbs the electrons, and so we have a non-vanishing interaction of the electrons with optical phonons. So just from this general form that we derived out of this machinery over here, we can extract some important consequences that scattering with acoustic phonons can be written in some approximations that we'll use later as essentially proportional to Q, and the proportionality constant will be some number, which is the deformation potential, and that's where the Baldinian-Shockley theorem will come in, multiplied by Q. Notice that this has as units of energy divided by length, which already tells us something which must be connected to how much the edge of a conduction band or valence band changes when I change the lattice constant by a given amount. On the contrary, for optical phonons, we just write it as some constant, which for reasons that I think a D implies that it's a deformation potential, so units of energy, the big K here tells you that you're dealing with a wave vector. So this is the standard nomenclature that is used in the literature. So this is an important consequence that I should have emphasized last time, and I forgot to do it. So keep that in mind. So we will use these two results of this particular asymptotic behavior in the limit of small q in calculating the electron phonon scattering rates in a simpler case of parabolic bands and isotropic bands, as usual. It's usually used. This is something that we discussed last time. It is the normalization of the Fock states for the bosons, concentrating on the boson part here, on the phonon part here, that gives us this famous Einstein's coefficient. The coupling AQ is, or the coupling AQ multiplied by the other terms that we have, gives us when squared, as it enters in calculation of the scattering rate, a term which is proportional to the number of phonons that we have for absorptions, and a term which is proportional to the number of phonons that we have plus 1 in the case of emission. So we recover stimulated and spontaneous emission out of simply the normalization of the Fock states. I give you the example of calculating, for example, where this normalization comes from. I encourage you to do it on your own. Look, for example, at the calculation of the normalization of the Fock states in which we have two bosons, two phonons in this particular case, how to use the canonical commutation rules to find what this is, and then use the induction principle to show that indeed this is generally valid, so that the states in which we have n phonons, n bosons in general, has to be normalized by an n factorial square root in the denominator. And so this is where these factors, these Einstein's coefficients, come from. And in particular case, if we look at the matrix element between of the annihilation operator between a state n, remember this, we destroy a boson, so we will have a state n minus 1, but there is a normalization factor floating around. The fact that this is normalized to n minus 1 factorial, square root, this is n factorial. So if we want to express it in terms of the normalization condition for the n minus 1 state, we have this factor n to the 1/2 floating around, which is what we have in this expression. And that's what indeed what we're calculating here. Okay. So now I told you, we can use nowadays, we can use DFT to calculate this coupling constant. I remind you, this A, script A, has this form if we use pseudo potential, but in general we can go back to a density functional theory, and then we can perform the calculations of the change of the total energy, and so the matrix element directly from the calculation of the total energy of the perturbed system. Historically, this, as I told you, this was not possible. So, and also there are, as I said, some issues with DFT, and there are some materials in which essentially we know more about what's going on. So how can we approximate, going back to the history, let's put ourselves in Bardeen's and Shockley's shoes in 1950s and say, how do I calculate this? How can I find out whether indeed, for example, the mobility that I measure in silicon crystals for electrons or holes is really due to phonons or something else? At the time, the problem was a little more complicated. As I mentioned, I think last week, the electromobility in intrinsic silicon was supposed to be something of the order of 350 centimeters square volt second, which is about a factor of 5-ish smaller than what it is. So the crystals were not particularly good. Nevertheless, the idea that Bardeen and Shockley had in 1950 was, we said what the electrophonon interaction is when we're dealing with nonpolar coupling, what we call the deformation potential. A phonon amounts, consider a longitudinal phonon, acoustic phonon, is a wave, look at it as a plane wave, of dilatation and compressions that are on a plane perpendicular to the propagation of the phonon, the direction in which the phonon propagates. This, seen from an electron which is sitting at some particular position in a lattice, looks like a time-dependent change of the lattice constant, or the presence of strain at the particular location. Presence of strain, change of the lattice constant, which is a uniform dilatation or compression, strain, if it is shear, biaxial, uniaxial strain, will induce a change in the band structure, which can be measured experimentally. And therefore, the electron will feel the bottom of the conduction band moving up and down as the unit cell, the size of the unit cell, changes by an amount u, which is the displacement of the ion, or that represents the propagation of the phonon. For a very small displacement, we can define a parameter, which is the change of the edge of the bottom of the conduction band when we change the lattice constant by a unit, multiplied by the displacement. This will give us the strength of the interaction. Notice this parameter has units of energy per unit length, which is indeed the same dimension, the same units that we had for our coupling, the coupling strength of the electron-phonon interaction. For purely dilatational wave, notice that in 3D, if we are in bulk, the change of the potential energy that we have associated with the displacement of the ions is proportional to the divergence of the displacement field. Clearly, if we displace all the ions by the same amount everywhere, we get nothing. It is how much the displacement out of equilibrium position changes from one position to the other in a continuum limit. So it will be proportional to the volume. The change of the volume that we have in a unit cell will be the volume multiplied by the divergence of the displacement field. If we assume that this is a plane wave, it will have a behavior e to the I QR. Therefore, this is proportional to Q. And indeed, we recover what we saw before. I mean, conclusion. For acoustic phonons, the strength of this coupling constant, coupling function, whatever it is, will be proportional to Q with a proportionality constant which must have units of energy. So the idea is that actually this can be written this way, where this deformation potential, unfortunately the term applies to both this as well as the product of the deformation potential times the Q vector. So it can have units of either EV or EV per centimeter, whatever. But this parameter in particular is what we call the band or distortion or strain deformation potential. Okay. And it is denoted by delta. I put acoustic here, it could be TA, LA. They're actually different. And they can be calculated, they can actually be measured. From elasticity theory, you can go and look at parameters which in the literature are called E sub 1 or Xi, this Greek letter Xi. Sometimes there are two of them in materials which have a conduction band minimum, which is along a point, a symmetry line, or at a point which is not at gamma. You can have anisotropic matrix elements. This is the case for silicon, that's why I mention it. And then you can have deformation potential, which are called Xi sub U for uniaxial strain, Xi sub D, which is the dilatation deformation potential, and the matrix element of expressing the electron-phonon interaction for acoustic phonon can be expressed in terms of these parameters. But the idea was, at the time, extremely important. Now that I can correlate somehow my matrix element that I know how to express formally, as we did in the previous slides, but I cannot calculate, I can express it in terms of a quantity, this deformation potential that people can measure. You can put a crystal, a silicon crystal inside a hydrostatic anvil. You compress the water is, as we know, is mainly non-compressible, so we end up compressing the crystal, and we can do spectroscopy on the crystal and see how much the absorption spectrum, for example, shifts in energy or in frequency. And this tells us how much the band gap changes under the application of strain. We can add other measurements by bending a wafer in some particular way, so applying uniaxial or biaxial strain, so we can have some experimental handle on these parameters that we can correlate with the expression for the mobility. And I will give you in a moment a specific example of a calculation of the electron phonon scattering rate, electron acoustic phonon scattering rate, in a simple approximation of parabolic and spherical bands using this deformation potential approximation. Later on, probably in a couple of weeks, we will discuss how this affects the mobility and how we calculate the mobility in the same limit. So now, having done that, so the result of all of this thing is that we can find a simple way to express the electron phonon matrix element. Let's ignore the overlap factors, the overlap integrals for intra-valley processes. So for material like gallium arsenide, like silicon, ignoring intervalley processes, electrons, if we want to calculate the mobility, are not too far away from an equilibrium distribution, by definition, around the minimum. So that the region of the Brillouin zone will be probably K and K prime is not very large. So essentially we can forget the fact that there will be a factor smaller than 1 that modulates our matrix element square due to the overlap between the periodic component of the block functions. So essentially, we can consider electrons as plane waves, forgetting the u's, the little u that we have in the expression for the block functions. So what we have is now the matrix element as a simple form. This is whatever is left over of the various creation annihilation operators. Those are the Einstein's coefficients, and we saw where they're coming from. So we have n+1 if we take the upper sign, which is for emissions. The n, of course, is stimulated emission. The 1 is spontaneous emission. For absorption, there is the minus sign, so the 1/2 disappear. This is just proportional to n. And then our matrix element becomes just the amplitude of the phonon displacement, which is the prefactor that we had here. Let me go back, this factor essentially. And we're expressing the deformation potential QV as our empirical parameter delta Q, okay, which is this. And this is already the squared of this expression. Here I mentioned the fact that actually for silicon, I thought it was worth mentioning because silicon is still important. It has been reaching its end point for the past 40 years, and people keep saying that. So it's important to notice that the minimum of the conduction band in silicon, it's actually 6 minima. They're not spherical, as you know, they're ellipsoidal. So we have two different directions, the transverse and the two transverse directions and the longitudinal direction. Things are indeed a little bit different. There was a analysis done by Herring and Fock shortly after Bardeen and Shockley came up with the deformation potential theory. I think they were all at Bell Labs at the time, in which they did some essentially perturbation theory, starting from group theory, and they represented this thing, which is this deformation potential, which we assume is isotropic, which means it doesn't matter where K and K prime lie in terms of their angles. It doesn't matter which direction Q goes. It's all the same. Okay, in silicon it's not quite so. And actually they represent this parameter, depending on whether you're dealing with longitudinal or acoustic or transverse. This should be a T. Oh boy, okay, another typo. This is a T. So with longitudinal or transverse acoustic phonons, you can express it in terms of those two deformation potentials that people can measure experimentally, the uniaxial shear and the dilatation deformation potential, and in terms of the angle that the phonon, which is emitted or absorbed, forms with the longitudinal axis of the ellipsoid. And this essentially tells you that for longitudinal phonons along one particular direction, theta equals 0, you only have a dilatation, as we saw before. Okay. Instead, if we're dealing with transverse phonons, we're dealing mainly with shear. So this uniaxial shear deformation potential. So this is, if you want, a small correction, but it's important to realize that when you look at the literature and you look at the effective values that people reported for this deformation potential, 9, 10, 12, 11, whatever you find, it's actually an approximation in all cases, and you can explain some differences depending on a particular situation that you have because of the anisotropy. For example, in bulk, in a strained material, or in an inversion layer where the electrons now are confined in 2 dimensions, the average that you take, the averages that you take will be different in the 3 different cases. And so you can expect some changes of these numbers. These numbers do not depend on strain by definition as long as strain is weak. They're, if you want, a representation of what strain does. Okay, for optical phonons, it's simpler yet. There's no Q dependence on the matrix element. It's just a constant. The only dependence of Q in principle may be entering via the dispersion of the optical phonons, but typically one assumes that optical phonons are dispersionless, flat. If you remember, they don't change much in many materials, although again, it's an approximation. And so one ignores the dependence on the phonon wave vector of the energy. Therefore, their Bose-Einstein occupation is also fixed. And this matrix element, at least in these approximations that we're dealing with, is a constant. If you calculate the scattering rate, we can actually get a very simple expression. I will not show the derivation of this particular equation here, but I will show you the derivation of the scattering rate with acoustic phonons, which is a little more complicated, but not much. Essentially, what you see is that we have a prefactor, which is essentially this parameter here. The volume here is just a normalization convenience here. If we go to infinite volume normalization, this becomes the usual 1 over 2 pi cube when we do the integration. That would cancel out with some delta function for momentum conservation. But we have a parameter which depends on the strength of the interaction. If we have this delta dk divided by omega op, the frequency of the optical phonon, and the density of the crystal. This comes from the amplitude or the displacement of one ion that we get from the canonical commutation rules. And then there is a density of state, practically the sum of these factors, the square root of 2, the pi, the 3/2 of the mass. You remember that the density of states in 3 dimensions is proportional to the 3/2 power of the effective mass, the number of phonons that we have, or for emissions or absorption, and then the square root of the energy of the final state, which you're scattering. For absorption, you go to the initial energy plus a phonon energy. For emission, the opposite, of course. So this is the density of the final electron states. And indeed, this is a general rule that scattering rates are controlled by 2 big factors. One is the energy or momentum dependence of the matrix element. In this case, we have none. And the second big factor is the density of the final state in which the electrons can go. Since we have no energy dependence here, we're left only with the energy dependence of the density of final states. By the way, of course, this term here is non-zero only when the electron has energy large enough to be able to emit a phonon. Otherwise, this term vanishes. So strictly speaking, I should have put a theta function, a heavy side theta function here. Okay, for optical phonon, things are a little bit more complicated because we have a Q dependence. Notice this is the matrix element for acoustic phonons. There is this deformation potential in eV per centimeter, which depends on Q. And this is, we cannot take it as dispersionless, because this is the dispersion of an acoustic phonon that a small q goes almost linearly to 0 with a proportionality constant, which is the sound velocity. Excuse me, transverse or longitudinal. So this was simple. We'll see how simple it is in a moment. For acoustic phonons, we have to do a little bit of more work. And the end result will be something that depends again on the density of states. So let me go through the calculation of the scattering rate, just to give you at least once, well, we'll do it again for the Frolic interaction, how to calculate the scattering rate. This was actually a little addendum that I prepared some time ago. So if we want to be a little bit more formal, the approximation that we're using for the electron phonon Hamiltonian will be the usual terms. This we will not need. We have already accounted them for by assuming that the electrons are a non-degenerate electron gas, so all final states are available for more practical purposes, and we always have an electron K that we consider exists already, is present, and this will be lumped into the Einstein's coefficient. So we can ignore these pieces. This piece, the time dependence in the exponential, we will consider it implicitly in dealing with Fermi-Golden rule. This is where this is coming from, and we'll have an h bar omega q in a delta function that represents energy conservation. So essentially, what we need in practice is only the spatial dependence, which is a plane wave, of this factor. And the factor would be the displacement of the ion, the h bar divided by 2 rho omega, multiplied by the strength of the interaction, which is the deformation potential. Everything to the 1/2, eventually we'll have to square it, so the square root will disappear in dealing with the scattering rate. So this is what we have, and this will come in simply in the integral that we'll have between initial and final states. So that's what I've done. So the matrix element can be written as an integral over this, and it will be just a sum over all possible q's of this, which you recognize immediately is a delta function expressing conservation of crystal momentum. These factors, which are the Einstein coefficients, when we will square it, square root will disappear, of course, and then the prefactor that we have explained before. So this is relatively simple. We have to plug it now back into Fermi-Golden rule. So we have to use this matrix element, we square it. Remember, this is a delta function for conservation of crystal momentum, so we'll be simplifying our interaction, and that's again the expression that I repeated. We plug it back into the expression for Fermi-Golden rule. The square of the matrix element between an initial state and a final state, K prime, the delta function that expresses energy conservation, plus or minus depending on whether we're emitting or absorbing a phonon, the famous 2 pi over h bar in front, and then we sum over all the final states. And we're assuming this, that already there is a momentum conservation represented by the whatever the delta function that we have here. Now, the problem is that this depends on Q, or if you wish, expressing it as a function of K prime, depends on K prime VI term, this Q squared, which will be K minus K prime, the magnitude of the momentum transfer. And this is a little bit complicated because this Q enters in the expression for the energy of the phonon, the frequency of the phonon, which in turn enters exponentially in the Bose-Einstein occupation factors that we have here. So the integral cannot be solved analytically unless we make some approximations. And there are some convenient and extremely common approximations. First of all, we're dealing with acoustic phonons. Acoustic phonons have an energy that goes to zero as small q. If we're calculating the mobility, for example, or electronic transport at fields which are not too high, the electrons populate a region of the Brillouin zone, as I said before, that is not very large, and it's around the minimum of the conduction band. The same for holes, if we're dealing with holes. So it's reasonable to assume that the phonon energy, or the energy of the phonons which are going to be involved in our transitions where K and K prime is not big, Q will be not big, will be small. So the energy of the phonon can be considered to be much smaller than thermal energy. So if we expand this in power series, the exponential, when T is very large, this we can expand it in power series of the exponential as usual, and we're left with the inverse of the argument of the exponential. And notice also that now this is very large because we're assuming this relationship. Therefore, n plus 1 and n are roughly the same. The one disappears because it's much smaller than the number of phonons we're around. So absorption and emission have the same strength, the same Einstein coefficients in this limit. Let's assume also that the phonon dispersion can be considered to be a linear form, and that's because we're not, again, consistent with this approximation, we're not moving very far away from Q equals 0, from the gamma point, so we can approximate it with the sound velocity. If we want to separate the longitudinal transverse phonon, we can look separately at the transverse and longitudinal velocity, just calling it C sub s, sound velocity. You pick whatever value you wish. So we can represent the NQ as KT divided by h bar CSQ, having simply replaced omega q with this expression. And finally, we have to deal with the fact that we have an integration over the delta function. There's a q coming in here. Well, E and EK prime are of the order of KT. Particularly if you can calculate the mobility, for example, it's really the electrons at the Fermi energy that matters. So in either case, if we assume that this is, if we neglect this term here, we don't make a big mistake. And therefore, one assumes that the interaction is elastic. So there is no energy exchange, okay? Again, it's okay if you're calculating the momentum relaxation, for example. Clearly, you cannot justify it so well if we're dealing with energy relaxation. But the momentum relaxation, which is what the mobility is all about, this is a good approximation. It simplifies the calculation tremendously because then our square matrix element, remember, it was this object here. Now notice what happens. There is a Q in the denominator coming from here because I'm approximating omega with CSQ. Since n also has an inverse dependence of q, we have a q in the denominator from here, a q in the denominator from here, and they both cancel the q squared that we have in the numerator. So essentially, we go back to the same situation that we would have if we were to consider optical phonons. The matrix element does not depend on q anymore. And this is what I've written here. It's simply a constant, so to speak. Of course, it depends on the strength of the interactions, so the deformation potential square. It depends on temperature. It increases with temperature. It's inversely proportional to the mass density of the crystal and to the square of the sound velocity. But it does not depend on Q. So if I plug it here, I can bring this stuff outside, and then I'm left with the integral over the entire Brillouin zone of E of k minus E k prime. But this is the definition of the density of states. Okay, a half, because I'm not considering spin. I'm summing over on only one spin, since I'm assuming that spinning is conserved in an electron phonon interaction. We can talk about it. There is a small component of interactions with flip spin. I think they're about some 4 orders of magnitude smaller in terms of the scattering rate that they give. So this is just the density of states, as you can see here. So the net result is that the scattering rate for an electron scattering with an acoustic phonon is given by an expression which depends on the square root of the energy. Again, we're assuming it's elastic, so this is both the initial and the final energy. And this is the usual thing, usual considerations that it's the density of final electronic states that mostly controls the strength of interaction. It increases its temperature. Clearly, the resistivity also will increase its temperature because it's proportional to the scattering rate, or vice versa. The mobility increases at local temperature, and it's proportional to the 3/2 power of the mass, simply because it's a term representing the density of states. Notice also that there is a square of the sound velocity here, which means that for transverse phonons, for example, we're going to have a stronger coupling constant in this expression. So if there are any questions, I would stop here. I think that we have reached the hour-and-a-half thing. So let's take the usual 5 minutes break. Let's meet at 5:02, for example. And again, ask questions, please. My usual question is, am I online? Do you hear me? Do I exist? Yes? No? Am I online? Yes?
Yes.
Good. It was beginning to sweat. Okay. Good. All right. So we'll see you in 5 minutes or so. Okay, shall we resume? Are you back? Not yet?
Yes, we're back.
Okay. So you see my slides, hopefully? Yes? Good.
Yes.
Excellent. Sorry about these nagging questions, but as I said many times, it's my nightmare. Okay. This is a plot of what you get by using that expression that I showed before. Notice one important thing. Since the interaction either is constant or it grows with Q, essentially we reproduce with the approximation that we have made for the acoustic phonons. We see the density of states, essentially. This is a semi-log plot, but you see how the interaction increases, the strength of the interaction increases with energy, with the square root of energy. Ignore this for now. I didn't change the plot, but we'll deal with it in a moment. So the density of final states controls this interaction completely because the matrix element doesn't play much of a role. The interaction also will be isotropic, essentially. If we look at the integration that we have over here, there's no Q, so we don't favor any particular angle. So it's totally randomizing. An electron scatters with an acoustic phonons or with an optical phonons with a nonpolar interaction. It can go into any state. It doesn't depend, the interaction or the probability of finding a final state does not depend on the angle between the initial and the final wave vectors, which is called the scattering angle. In this particular case, the wave vectors are also parallel to the velocity, so it's really the velocity relaxation that is totally randomized. Okay, just to show you what happens if you go a little beyond, these are very old results that we got for scattering with electrons and holes in silicon at various temperatures. You see, of course, the temperature dependence. That is not surprising. We had it in a matrix element. You see that at the beginning you have something like a square root, but then at some higher energies, our approximation of considering the band structure is purely parabolic breaks down. Actually, non-parabolic correction can be important at relatively low energies in silicon. And you see that essentially what you have is the density of states. You have a hump over here, which is the presence of the satellite L values, and then some peaks that you can find also in the density of states. If I show you the density of states calculated with DFT or empirical pseudopotentials for silicon in a conduction band or in a valence band, you would have curves which have essentially the same shape. May change a little bit, but peaks at the same points, at the same energies. So the density of final states, that's a crucial thing to remember, is one of the two major causes or essentially terms that affect the scattering rate. Fröhlich interaction. I'm not going to go into too much detail. You have the slides, you have the text, but essentially what we have to do, the major thing is, okay, we can use density functional theory today, very good, except that even density functional theory for polar interaction is a little tricky, because for density in DFT you use supercells or cells, and here you have to deal with a long range interaction. So it's an electric field which extends over many cells. So your calculations are always a bit tricky because you have to consider what happens at large distances. This can be done in many ways, but it presents some problems. So one has to be a little bit careful even in DFT. Anyway, DFT does it now. More accurately, I would say, than the non-polar interactions. What we can do instead is follow the same kind of techniques that we used, if you remember, when we were dealing with the amplitude of the potential due to a plasma in second quantization, with the similar situation that we saw for the electric field associated to a photon, the displacement of an ion due to a phonon, and so on. We could use a canonical quantization procedure, which would be a little bit cumbersome in general, but you can follow it. Or you can follow that argument by Alan Stern and Ferrell, which I call the semi-classical quantization procedure. So what we do is, let's consider what is a longitudinal optical phonon. By the way, remember, electron scatters only with longitudinal modes. I gave you the argument in the past. Ask me again if you don't remember it. So only zeros of the dielectric function of the system give you the longitudinal modes, the frequency of the longitudinal modes, and only these longitudinal modes can give rise to an internal electric field which doesn't vanish because the dielectric function is zero. So you get the displacement electric field D equals zero, even if E, the electric field, is non-zero. This is the basic argument. So let's consider only longitudinal optical phonon, and let's assume that the potential associated with this phonon is this form, this particular form. Some amplitude, we don't know yet what, and then the usual plane waveform. It oscillates in space with a spatial frequency given by Q, so a wavelength which is 2 pi divided by the magnitude of Q, and the frequency omega LO. We can calculate now the total energy which is associated with this. It should be zero classically, okay, but then we'll do a semi-classical, semi-quantum trick to see what it is, and so finding this amplitude. So if this is the potential, we can look at what is the charge density associated with this potential. It is just epsilon, and this, remember, depends also on epsilon. And of course, this is Poisson equation. So the Laplacian of the potential will be the charge density divided by epsilon. We look at the total energy associated with this eigenmode of the system, with oscillation of the charge density associated, of course, with the displacement of the ions and the electrons due to the presence of a longitudinal optical phonon, and use the virial theorem as usual, because this is a Coulomb force. So the total energy time average is equal to twice the potential energy, which we can calculate in various ways. One way is just to integrate over the entire volume omega the product of the charge times the potential. This is actually electrostatic potential, not the potential energy, sorry. There is a charge implied over here. And we can just do the simple calculation using this form. The integral over time will give you a 1/2, and then we have a factor of 2 over here. We integrate over a period, this over the entire volume, the cosine. We get an average of 1/2. So at the end, we find that the total energy associated with the presence of a longitudinal optical phonon is given by the dielectric function times q squared times the amplitude square of the potential, the oscillation. Classically, as I said, this is zero because epsilon is calculated at the frequency omega LO, and it should be zero. But quantum mechanically, we know that the ground state of a system, this is an oscillator, a harmonic oscillator, cannot be zero. So we set this energy equal to, okay, here I've done it in a different way, to the 1/2 omega LO. We actually can do it in a really different way now, because this is what we did to calculate the potential of a plasma. Here, this potential will be due to all possible excitations that we have in a system. Can be plasmons, can be longitudinal phonons, optical phonons, or anything else. So we want to isolate the contribution of the potential which is only due to the longitudinal optical phonon. Remember that the optical phonons change the epsilon. When they do not respond, epsilon will be what we called epsilon infinity, or sometimes we can call it epsilon high, means at high frequency, the frequency higher than omega low. When the frequency is lower than omega low, then we have the static dielectric constant, if you want, epsilon 0. So what we can do is actually isolate, if we wish, the potential due only to the optical phonons themselves. So we write Poisson equation instead of the way I wrote it before by subtracting the charge that we have when the phonons do not respond from the charge that we have when the phonons respond. This will give us only the potential associated to the longitudinal optical phonons. So if I define the inverse effective dielectric constant as 1 over epsilon high minus 1 over epsilon low, which is this quantity, I will get from this expression, now replace epsilon with this epsilon bar, which is this effective epsilon, which isolates the contribution of the optical phonons. Let's set this equals to 1/2 h bar omega LO, which is the ground state energy of the harmonic oscillator that oscillates with this particular frequency. And then we find that the square of the amplitude of the potential, which is my scattering potential, which is what will go into the polarization that we want to use to couple the electrons with this particular excitation, will be inversely proportional to q square, and then to this 1 over this epsilon bar, which is this effective dielectric constant, inverse dielectric constant. So this is the way that I think sort of the way Fröhlich derived it in those two papers. This actually is a book that, again, I couldn't find, so I cannot confirm. I just look at Fröhlich himself refers to this book that he had published. The paper in 1954 that I gave you in a reference I gave you before is what we call the Fröhlich coupling now. So the interaction of the Hamiltonian that expresses the interaction between the electrons and the longitudinal optical phonons will be this coupling constant. Okay, it's a function of 1/q square. This is the square, so we have to take the square root. And then the usual terms, creation and annihilation operators that express the interaction between an electron and a phonon. So this will be the vertex, if you wish, that replaces the deformation potential times the amplitude of the ionic displacement that we had for non-polar interaction. Notice clearly for materials which are non-polar, this is 0, because the optical phonons do not change the dielectric constant because they do not contribute to the polarization. They do not generate an internal field, nothing polarizes. So this interaction vanishes in non-polar covalent materials. In polar materials, the dependence on the transfer momentum or crystal momentum that is exchanged between electron and phonon is the opposite of what we have, the opposite qualitatively, of what we had for the non-polar interaction. For the scattering with acoustic phonons, this thing was a dependence on q square. This is now 1/q square. So completely the opposite behavior, and that has important consequences. The algebra is a little more complicated. We have to calculate the electron phonon scattering rates with this thing. Again, this is the usual matrix element expressed in its full glory, accounting for the factors of the phonon occupation factors, the electrons occupation factors. As usual, we simplified. We consider only the non-degenerate electron gas. So n over here can be ignored. It means we always have final states which are available because they are not filled, or they're filled to such a small amount that we can ignore it. And we consider only the scattering rate for an electron that already exists. So this will be 1. So we can ignore the Fermi functions, if you wish, of the electrons. The occupation number of the phonons will be expressed by the usual thing, the usual Einstein's coefficients, because we have the same matrix element that we had previously for the non-polar interaction, the same expression in terms of creation and annihilation operators. All the differences are in the coupling constant or coupling function. And so we can express, for example, emission with the Einstein's coefficient due to the emission. And then we have the usual integration using Fermi golden rule, 2 pi over h bar. These are the constants of the matrix element that these guys that have taken out. And only thing left inside the integral will be the 1/q square. And this is the usual expression for the energy conservation with the Dirac delta function. Okay, the integration is a little more complicated. This is a 3-dimensional integral. One dimension goes away, the integral over the azimuthal angle. If we take a coordinate system in which the initial wave vector is along the z-axis, the final wave vector is at an angle, the azimuthal angle phi and polar angle theta. Nothing depends on the azimuthal angle phi, so we simply get a factor of 2 pi when we integrate expressing in polar coordinates. We have to worry about the energy conservation. This is a little trickier. This is the usual expression delta theta sine theta that we get going from Cartesian to polar coordinates. to spherical coordinates, I should say. And then we have the delta function, and I've expressed explicitly now the energies using the parabolic band approximation with an effective mass m star. And the energy that we have here will be h bar squared k squared divided by 2m star, which cancels with the term coming from the square of this term, and we're left with the mixed term, which are proportional to q and q squared. Remember the properties of the delta function. The integral will give a non-zero contribution only if the argument q and theta of the delta function has zeros inside here. So we can find the two zeros of this of the argument of the delta function, and which were called which are expressed over here. So only if having re-expressed everything in this term by changing the integration variable over the angle theta to this variable x now, only if x hits the point b, which is whatever is left over here, we're going to get a non-zero component. This has two solutions. We find two zeros, q plus and q minus, the two zeros of the argument of the delta function. So we integrate over this angle variable x that we have now, and I'm just rewriting using some algebra in terms of the energies, expressing the k in terms of energy. K will be just the square root of 2m star e divided by h bar, and we can perform the integration. And the integration again gives you a non-zero contribution, only q goes between these two values, and you can do the algebra relatively easily, and we find this expression. This is simply integral over q. Okay, again, I've put here explicitly the Heaviside step function, saying that this expression is non-zero only if the electron energy is bigger than the h bar omega law. So if the electron has enough kinetic energy to emit an optical photon. So no problem about the square root here becoming non-zero. If we look for absorption, it's exactly the same, except that now we have a plus, and the expression is the same. So the scattering rate depends, and that's the crucial thing now, of course, on the strength of the interaction. This is sort of proportional to the oscillator strength, or the F strength of the optical phonons, how much the optical phonons contribute to changing the dielectric function as a function of frequency. It depends on effective mass. This is a remnant of the density of states. And then we have a square root of the energy in the denominator. The square root of the energy is essentially a combination of two factors. The fact that the matrix elements here depends on q square matrix elements, depends on 1 over q squared, gives me an energy in the denominator. But I still have the density of states to factor in, which is the square root. And so I end up with the dependence, which is 1 over the square root of the energy at large energy. At low energy, actually, the density of states dominates. And actually, if you expand for e going to 0 in this particular case, expand the logarithm, you see that you have a term which is increasing with energy. So this is something that I will not discuss now. It's related to accounting for non-parabolic effects. But the bottom line is that in this picture, it's the same picture that I showed before. Look at what we saw before for the non-polar scattering. It grows with the density of states. The polar interaction now, okay, notice the step here. This is particularly for gallium arsenide, in which I'm assuming that the frequency of the optical photon is about 36 milli-electron volts. That's where we see the step. It's the onset of emission. Here we have absorption. It's not clearly visible, but it grows because of the density of states effect that dominates at small energy. And then it begins to drop, going with inversely proportional to the square root of the energy. And that's, again, it's the product of the 1 over E that you get from the matrix element and the density of final states, which is the usual factor that enters the expression for the density of states. Now, notice that the scattering rate for the non-polar interaction keeps increasing. For the polar interaction, it hits a maximum and then it decreases. This has extremely important consequences. This is a subject that goes back to the 1940s or even earlier. Actually, one of the early papers by Froelich the famous 1935 paper in the Proceedings of the Royal Society, dealt with the dielectric breakdown in polar materials, which are insulators. They're all dielectrics. And the reason is, in those materials, the nonpolar interaction is not very strong, so we can ignore this. They come down at lower order of magnitude in here. The main process that controls electronic transport at high field is the polar interaction, is the Froelich scattering. So now the consideration that has been going on for a long time, trying to explain dielectric breakdown. Dielectric breakdown is the process, the phenomenon in which if you apply an electric field large enough, eventually your insulator becomes leaky. It begins to conduct current. It means different things to different people. It can be reversible electric breakdown. You just induce an avalanche, if you wish, from which you can recover. It can be destructive in some cases. When you break silicon dioxide, you break it for good. Actually, I used to be an experimentalist in the early days and had fun breaking silicon dioxide layers. You can actually see them breaking down. You can see the aluminum contact on top of your MOS capacitor boiling and creating pinholes. And that's due to a runaway effects in which you create a weak spot in which there is more current. Joule heating creates even more, a higher current, and eventually the crystal breaks down structurally. Instead, you can have recoverable breakdown when you have simply an avalanche process. But the idea is the following. If you apply an electric field, which is smaller than such that the field is such that the energy gained over a mean free path, which is the average distance projected along the direction of the field. So the mean free path is the distance that the electrons travel without collision. Over this distance, it can gain energy from the field, and its energy will be lambda times F times an electron charge, if you wish. As long as the field is small enough, such that the energy gain between two collisions is smaller than the energy that the electron loses in a collision, you're okay. But if the field begins to be strong enough, it may so happen that a few electrons begin to gain from the electric field more energy that they can lose. So as they move along this line, that they move towards the right, and they go towards a higher scattering rate. That's good. If this were continuing forever, there would be no problem. But at this point, you reach a maximum. So if an electron now reaches an energy which is above, what is it, 150, 120 millielectron volts, something like that, above which the mean free path begins to increase, then what you have is that the energy that you can gain between two collisions gets bigger than the energy that you can lose. So the electron will end up gaining even more energy from the field. And as it moves and it gains energy, the mean free path grows more and more. So the energy that it can gain from the field increases even more, and it scatters less frequency because it scatters less frequency. And eventually there's nothing that prevents the electrons from gaining an infinite amount of energy. Infinite is in quotes. Some effects may come in, although we said that the nonpolar interaction is weaker in some materials, like aluminum oxide, for example. Still, at some point, the density of states may be such that, may increase so much that acoustic phonon scattering may come in and intercept the polar scattering rate. In this case, the electrons will be controlled by acoustic phonon scattering, which happens in some ways in silicon dioxide. But in other materials, this may never happen. Or what happens is that the electron may gain enough energy to generate an electron hole pair across the gap. So it takes an electron from the conduction band and move it up to the, from the valence band and move it up to the conduction band. In this case, you begin to have the onset of an avalanche, because now the new electrons and the new holes will be accelerated in the electric field. The same process will repeat again, and this new electron and new holes will generate another pair, each of them in turn, and this new pair will generate new pairs, and you see that you have a runaway effect. And this is a classical model of, I shouldn't use the word classical, a usual conventional model for dielectric breakdown in polar materials. In non-polar materials, it's the same process, but you do not have this velocity runaway or electrons runaway, which happens when you hit the maximum of the scattering rate for polar interaction. So this is an interesting consequence of, if you wish, this idea that the matrix element actually gives you a 1 over a square root of energy contribution to the scattering rate. You have it for all Coulomb interactions, because most Coulomb interactions have some power of Q in the denominator in their matrix elements. And so when you integrate, you get a dependence, which is the density of state multiplied by some negative power of the energy. And so it can, the last factor can win, as it does in this case. And so you have a scattering rate which decreases it increasing energy, and they give you the general argument for a Coulomb interaction. An electron at large energies doesn't care about the scattering potential anymore. So the larger the energy, the less and less will be the effect. Okay. One interesting thing that I want to spend a little bit of time, but not too much, is we talked about dielectric screening last time. And we talked about plasmons. I remind you that we found, for example, an expression for the dielectric function in the long wavelength limit, which I will show in a minute, review in a minute. And we saw that at long wavelength, the electron respond as a collective object, as a whole, by oscillating back and forth with the plasma frequency. Now consider an electron that is moving in a polar material in which there is a large density of electrons, either because you have doped it to a high density, or because you have gated the material. You are in a field effect transistors, and the gate bias has induced a large electron density. Now what we have is two types of long-range fields that can arise from elementary excitations of the solids. The field that we just saw, which is the dipole field due to the longitudinal optical phonons, and the long-range field due to the plasma oscillations. When the frequencies associated with these two modes, remember the plasma frequency grows with the square root of the density. The longitudinal optical phonon frequency, we take it to be a constant. When they begin to be comparable and approach to each other, we can expect something interesting going on. What is this? You have a phonon, the phonon creates a dipole field, this dipole field oscillates at a frequency that resonates with the plasmons. So now the plasmon respond, and the plasmon induce a dipole field, an electric field that can excite the phonons. It resonates with the phonons. So you end up with a top sort of excitation, which is a hybrid. It's neither a plasmon nor a phonon. If you wish, it's a dressed plasmon, or sometimes it's called the hybrid coupled plasmon-phonon interaction, phonon in a mode. So it's a new type of elementary excitations. One can do very fancy theory here, use what they are called Bogoliubov transformations that I will show them dealing with superconductivity later on today or next week. And something interesting happens, but it's interesting to see what happens to the scattering between electrons and these phonons that we can view now as dynamically screened by the plasmons, that the other electrons in the gas tend to respond to this. So how do we find what these excitations are? Remember the general rules. Excitations, the longitudinal excitations of a system are given by the zero of the full dielectric constant of the system, dielectric function, I should say. Now, in the long wavelength limit, the dielectric function of our doped gallium arsenide, for example, will have a term which is epsilon infinity, forget this for now, plus this term, which is the resonance due to the optical phonon. But now the epsilon infinity is modulated by the plasma response. So this, if you want, is the polarization of the plasmons, the epsilon infinity times this. The 1 is just the response of the valence electrons. And then you have the polarization of the optical phonons. So you have the 1, the polarization of the plasmons given by these terms, or the polarization of the phonons, which is given by this term. So now, if we set this equal to 0, we're going to find a frequency or frequencies of two modes that represent these coupled hybrid objects which are neither fully plasmon nor fully phonons. We can just do the algebra. It's relatively easy. We find the second-degree quadratic equation, and we have two solutions, which are given by these expressions. As the density goes to 0, we find that these two frequencies merge into a single expression, which is either 0 or the longitudinal frequency, the phonons frequency. So as the density goes to 0, we recover just the longitudinal optical phonons. The other frequency, the plasma, disappears because the plasma frequency depends on density. In this limit, disappears. When the density grows very big, though, something interesting happens. We have two branches now, very separate. One is essentially a plasmon-like frequency, and one is the frequency of the transverse optical phonon. I show it here. These are the two solutions. The red ones will be the TO and DLO frequencies. Again, they're split. Remember the Lydane-Sachs-Teller relationship. The ratio of the two is given by the square of the ratio, sorry, the square root of the ratio of the epsilon 0 divided by epsilon infinity. So these are the two frequencies of the longitudinal optical phonons and transverse optical phonons that we have in an undoped system. This is the plasma frequency that we would have in absence of longitudinal optical phonons, which clearly can never happen. But this is what we'd have ideally. When you couple them together, you get essentially the two bands, so to speak, repel. Remember, this is the usual rule, bands repel, dispersions repel, so they avoid the crossing point, and instead you start with the frequency of the longitudinal phonon in the upper branch and merge towards the frequency of the plasmons. At low frequency, you follow the plasma frequency at low densities, and then you approach the frequency of the transverse optical phonons. Why? Because the density is so high that the longitudinal modes are screened out completely. And so you lose the longitudinal optical phonons. Okay, so these are the two solutions. There is a simple way to calculate for each of these branches what is the fraction of plasmons or phonons that you have in each of them. The content of the phonon, for example, is given by look at a branch, omega plus, omega minus, see how far away it is for the plasma frequency. If it's exactly the plasma frequency, the phonon content will vanish. The farther away it goes from the plasma frequency, the stronger will be the phonon content, and vice versa for the plasmon content. And I show here indeed that the omega plus starts as a phonon. This is the phonon content, starts as a phonon over here, and at large densities begins to be a pure plasma. Okay, so this is a semi-log scale. So the plasmon content, which is 1 minus this, will be approximately 1. The opposite happens for the omega minus. The omega minus starts off as a pure plasmon, so the phonon content is essentially 0, and then it merges to a phonon. It becomes almost a phonon. Okay. You can calculate the scattering rate in a way which is very similar to what we did before. We can calculate the scattering rate, the longitudinal phonons, by looking at the usual Froelich coupling, but then you have to multiply by the phonon content. So you can scatter with both modes, but you can scatter only with the phonon content of that mode. And if you calculate the scattering rate, you see that indeed the total scattering rate is given by this solid line. I don't plot it here, unfortunately I should have plotted, but notice that the scattering rate grows beyond what you would get from the unscreened Froelich interaction. And this process is a strange process which is called anti-screening. What happens is that there are some particular frequencies or some particular densities in which the plasmons try to screen the phonon but lag a little bit. And by the time they get there, the plasma frequency is slightly lower than the phonon frequency. By the time they get to the position where they would like to be in order to screen the potential, which is a positive magnitude in that case, if you're dealing with electrons, they get there essentially half a cycle later. And so they end up actually enhancing the interaction rather than reducing it. So it's a strange effect, but what you can do is now do exactly the same thing at an interface between a semiconductor and the dielectric. So this is something that I think I may show, or I will show in one of the homework assignments, but I give you the solution here as well. Suppose start by considering a metal, but the metal has a surface, and then there's vacuum beyond that. So what is the plasma frequency that we have? Well, in the bulk, we will have the usual plasma frequency, but we will have at the interface another possibility. We have the possibility of having a potential which is localized to the interface. So if the interface is z equals 0, so the interface is on the xy plane, we can look at an oscillation that decays exponentially as you move away from the interface. You saw Laplace equation here. Remember, it's Laplace equation because these are eigenmodes. There's no external charge. So we go and look at what happens, and we can find out what is the frequency of the oscillation that would correspond to such a peak of the potential just at the interface. What we do is consider the Poisson equation. We have the magnitude of the electric field parallel to the interface, the magnitude of the dielectric, the displacement electric field D perpendicular to the interface. They have to be continuous. So it has to decay away from the interface in the metal and in vacuum, and with some amplitude. Okay, we find the boundary conditions for the continuity of the field parallel to the interface, the continuity of the D field perpendicular to the interface, and we find that the solution of this system is permitted only when this object, which we can call the total dielectric function of the system, the frequency of vacuum, which is whatever we have on top, and the frequency of the metal is equal to 0. This is the general rule. If you want, it becomes a secular equation, but it's a general rule that the longitudinal modes of the system, whatever they might be now, are given by the 0 of the dielectric function of the system. And this is the dielectric function of the system at the interface. Of course, in addition, we would have the dielectric function of the bulk, which gives us the usual plasmas. And notice that in this case, the solution of this system gives us something which is similar to what we have. We find that the frequency omega that satisfies this relationship is the plasma frequency divided by the square root of 2. So the frequency of a surface plasmon, the plasmon that propagates at the surface of a metal or any bulk electron gas but chopped off by the presence of a surface with vacuum, is equal to square root of 2 is essentially the relative dielectric function of the vacuum plus that of epsilon infinity of the metal, of the semiconductor. What happens if we have now an interface between the metal and the dielectric, or this dielectric on top, which has some phonons, and our metal on the bottom? So we have aluminum covered by silicon dioxide. What happens? Now something very interesting happens. This expression, the epsilon 0 now is, which is the vacuum, now is replaced by this dielectric. And for the dielectric, we can write the usual expression for the response due to the ions, which is this usual expression. So now we replace epsilon 0 with this epsilon I of omega. Epsilon 2D is, for example, the two-dimensional electron gas that we have in an inversion layer of silicon. So, for example, we have silicon with silicon dioxide on top. What happens now? We have exactly the same situation that we had in doped gallium arsenide, in bulk polar materials in the presence of a density n of free carriers. Now the roles of the density is replaced by Q. The plasma frequency, as you may not recall it, so I'll remind you here, we saw it briefly when looking at two-dimensional screening. The plasma frequency of a two-dimensional electron gas, our silicon inversion layer, is proportional, of course, to the square root. Remember, there's a square here. So the square root of the density, but also depends on the wavelengths of the plasmas, something that we don't have in the bulk. This is essentially the same expression we have for bulk. Dimensionally, you want a three-dimensional density here, so we have to take the two-dimensional density divided by a length, which is multiplying by Q. So that's a simple argument why it has to go like this. for dimensional reasons, okay? So now what we have is we find that the excitation at the interface of the system, which are these coupled modes of the optical phonons in the dielectric, the SiO2 that we have on top, and the two-dimensional plasmons that we have in the two-dimensional electron gas, our silicon inversion layer, or a two-dimensional material if you want, even graphene, it will be exactly the same. Graphene is a little bit different because plasma physics is slightly different. Graphene has no effective mass, it's a Dirac dispersion, but some material like transition metal like chalcogenides that has a two-dimensional plasma response of this type, we have to set the sum of these two equals to 0 because we can follow exactly the same procedure that we have here, except that is epsilon 0 and epsilon m. Now this will be replaced by the epsilon 2d, which is the two-dimensional dielectric function of the silicon inversion layer, and this will be replaced by the dielectric function of the insulator that we have on top. So we do exactly the same thing. The algebra is a little messier. It's fourth degree in omega, but actually it's not because there are no odd powers of omega. So this is actually quadratic in omega square. And we have two roots, rather complicated. So I'll show you the result. What we have is something extremely similar to what we had before. We have the omega TO and omega LO. It's exactly the same thing that we had before. This would be a funny thing, which is the frequency of the optical modes on an interface if they had no plasmons. Let's ignore that for now. This is the plasma frequency as a function of Q for the two-dimensional electron gas if there were no silicon dioxide on top, no dielectric on top. Notice that this is exactly the same plot that we had before, except that here I have the Q vector rather than the density. It's exactly the same features. What we have when we couple the two is the dispersions do not want to cross, they repel. So we have a mode which starts off mainly as a two-dimensional plasma, emerges into a phonon, and this is the mode which starts off as a longitudinal optical phonon and becomes a plasma, a two-dimensional plasma. And these are the coupled modes that we have. This, if you want, is a way to deal with dynamic screening of the Froelich interaction of electrons in the bulk, as we saw before, here in a two-dimensional electron gas. This could be a quantum well in your quantum cascade laser, for example. It would be exactly the same thing. So there are not far-fetched arguments here. The scattering rates of the electrons with the longitudinal optical phonons now changes. Notice how much it increases because of dielectric screening. This is the scattering trend with plasmons, and this is the scattering rate with the longitudinal optical phonons. One word of caution, if you're interested in transport, you're interested in the mobility, you say, boy, this scattering rate with the plasmons is huge, so the mobility would be totally destroyed. Well, it's not absolutely not the case. And the reason to keep in mind is that plasmons are oscillations of the entire electron gas. So view this as your electrons in a silicon inversion layer, electrons in your indium gallium arsenide quantum well in your laser. You want them to move. Maybe your high electron mobility transistor, better yet, and you really want them to move fast. If an electron in the electron gas, which is the channel of the material, scatters with a plasmon, nothing is lost in terms of the current. What you do is you simply take the momentum of one electron and distribute this momentum among all of the other electrons in this collective motion, which is the plasmon. So you don't lose momentum, which means you don't lose current. That's why one has to be extremely careful about dealing with the electron-plasmon interaction. The electron-plasmon interaction does essentially nothing at zeroth order. It just redistributes the momentum from one electron to the other electrons in the gas, in this collective motion of all of the other electrons. It changes the energy of a single electron, so the electron distribution function in terms of K space or energy will be affected by that to some extent. And this may cause some changes in the way electrons scatter with interactions in which momentum is dissipated. So there is some effect. but it's not a major effect. It's a second order effect, if you wish. So this huge scattering with the plasma should not be taken as a tragedy, because it's really doing nothing in this particular case. And this, you see the same thing, the phonon content. You see that the dispersion, the upper high frequency dispersion starts at the phonon, becomes a plasma, so the phonon content drops. The opposite happens for the for the low frequency branch. Okay. How much time do we have? Okay, we have some time here. Good. So, any question about what we've done so far? So let me recap it a little bit. We started off by talking about what happens for the dynamic screening of the Froelich interaction of electrons in bulk. We saw that we had to solve a problem in which the total dielectric function of the system is 0. This gives us the frequency of the longitudinal modes. Now we have two modes, and these two modes result from the coupling, hybridization, whatever you want to call it, of the plasmons and the optical phonons. And we saw what they look like, and they depend on the density, because the only thing that changes is the plasma frequency. The optical phonon frequency is fixed once and for all, once we fix the material. So the density changes, this changes the plasma frequency, and we had these two modes. If we go at an interface between a metal and a two-dimensional electron gas, instead we have a more complicated situation, but again, we have that the total dielectric function of the system, which is the dielectric function of the metal, of the dielectric, sorry, and the dielectric function of the two-dimensional electron gas had to adapt to 0 in order to solve the continuity of the potential, if you wish, and the continuity of the displacement field, the vertical derivative of the field multiplied by epsilon. You see that in order to have continuity of this, we must have the sum of these two has to be equal to 0. Okay, so this must be equal to this at x equals 0, which means that the sum has to be equal to 0, which somehow loosely I call the total dielectric function of the system. But it comes from the continuity of the D field, having assumed, of course, that the potential, and so the E field, the parallel component of the E field, are continuous. So setting this to 0, the sum of these two to 0, gives us now exactly, something which is very similar, analogous to what we saw in bulk gallium arsenide, with two dispersions that now depend on vary because the plasma frequency varies, and this varies with Q. And you see that you have these two modes, the phonons and the plasmons, that interact very strongly in some particular range of Q. At very small Q, so very long wavelengths, essentially the frequency of the plasma is so different from the phonon that phonon frequency do not interact. Similarly, at very short wavelengths, the phonon and the plasma frequency are very different, and in a region where they are similar, then there are some interesting effects. Any question about this? No question. Okay. Now, so this is a little bit of a digression. This course is supposed to be something related to the theoretical foundations, physical foundations of semiconductor and devices and so on. Nowadays, there is a growing interest in quantum computing, about which I know next to nothing. But one of the possible implementations of qubits, in terms of, in practice, what hardware do you build, is due by Josephson junctions, which are superconductors. So we'll not go into details. I'll give you an overview of where we stand with the transition temperature superconductors nowadays and how they've been used in quantum computing a little bit. But what I want to deal with is explain what superconductivity is, the conventional superconductivity. By conventional, I mean the BCS theory, the Bardeen-Cooper-Schrieffer theory. Because it's mediated by phonons. It's mainly due to phonons. And we just saw the electron-phonon coupling. So we can look at what happens in particular materials, metals, but not necessarily metals, when the electron-phonon interaction is very strong. There are bad effects due to the electron-phonon interaction because it suppresses the mobility, but when it's very strong, actually, you can go the opposite way, and there can be a coupling which leads to a total reduction of the resistivity, the killing of the resistivity. Superconductivity, as you know, was observed 110 years ago, and it's a sudden drop of the resistivity that you see in some metals when the temperature drops below some critical temperature. This is not a reduction of the resistivity. That would have been interesting by itself. Is even more mind-boggling. The resistivity really drops to zero. I'm not sure what is the experimental situation. They have a superconducting ring which has been carrying current for I don't know how many years, trying to see what zero means. What is the real experimental upper value that resistivity can have to be consistent with experimental results. So let's consider it absolute zero here. Okay, there are lots of interesting effects when the resistivity suddenly drops to absolute zero. One of them is, for example, the Meissner effect, which is if you have a material and you apply an electric field, if this metal is there, okay, the electric field goes into the metal, but once the material becomes superconductive, the metal is expelled. Actually, I'm not going to go to details, like details in quotes, like two types of type A and type B, type 1 and type 2 superconductors, in which some of them expel the field if it's applied before, some of them only don't accept it when you try and apply it after superconductivity, but is induced, but they retain the field as frozen if there was a field present before they went superconducting. The theory had to wait for quite a bit. From 1911, when it was discovered, there were some phenomenological theories developed mainly by the London brothers using classical electromagnetism. It was not an explanation of superconductivity. It was essentially an electrodynamic analysis of what are the consequences of having a superconductor, how it behaves. There was a semi-quantum mechanical theory by Landau and Ginsburg in 1950. Semi meaning they assume that there is a collective quantum state that obeys some generalized Schrödinger equation and see what the consequences are in a superconducting state. But the nature and origin of this collective quantum state was not obvious. The microscopic quantum theory fully was developed because, thanks to chronologically contributions by Cooper, mainly the Cooper instability, and I'll give you a flavor of what this is about. So the formation of Cooper pairs by Schrieffer, and finally by Bardino, pulled everything together in the coherent theory. I think that David Pines also contributed a little bit. He was one of the authors that actually first reached on not speculating, but on drawing conclusions and interesting consequences of the BCS theory shortly after the Bardeen-Cooper-Schrieffer paper was published. This was for, I apologize, my clock, 11. Okay, we're done. Thank goodness it's not a 24-hour clock. This was for superconductors that exhibit this transition temperature at very low temperatures, the order of few degrees Kelvin. In 1986, some new materials, mainly cuprates perovskites, were discovered by Bertnotz and Müller with temperatures in the tens of degree Kelvin, and nowadays at 1 atmosphere of pressure, I think we're up to about 150. There's been a report recently of a superconducting temperature of 288 Kelvin, which is a warm room temperature, not too warm, but room temperature, above room temperature, but at very high pressure, extremely high pressure, 250 gigapascal, if I remember correctly. I will show a plot later on. The idea is, of course, to have room temperature superconductors because they can be used for quantum computing, circus devices and so on, in competition with other alternative ideas of implementing qubits that I will briefly mention later on. I've been interested in this thing essentially in two-dimensional materials, particularly some electron-phonon interactions in graphene induced by a substrate, similar to the coupling with these modes, the hybrid plasmon-phonon coupling that we saw. Coupling with flexural modes can actually give an electron-phonon interaction which is so strong, if not killed by other effects, of course, that remains the practical consideration, that you can have actually superconductivity in many of these two-dimensional materials, which will make it extremely interesting for quantum computing devices. So that's an interesting subject. So what is BCS superconductivity, the conventional superconductivity? So you have an electron, it's traveling in a metal, in a solid. We'll see why a metal is convenient. As it travels, it polarizes the medium. You view this polarization as either an obvious way, this is a polar material, gallium arsenide, the electron comes, it interacts via the Furling interaction with longitudinal optical phonons, which essentially means that the ions polarize. Positive ions will be attracted by the negative charged electron, negative ions will go away, electrons will be pushed away, electrons in the bonds that constitute the material will move away. View it also as a non-polar. Non-polar really doesn't really mean that it's not Coulombic. Everything is Coulombic. So really this can be a strain wake, and strain can still induce some polarization in the material, okay? So view it as a wake of polarization objects. So view it, the easiest way to view it as in a polar medium. So we're in a metal where really you are polarizing electrons and ions, and the electrons goes by and leaves this wake of positive charge along the trajectory the electron was following. How long does this wake last? Well, if we assume that it's a wake due to some Debye model for the phonons, it's typically of the order of the inverse of the Debye frequency, which is roughly the size of the unit cell divided by the sound velocity. So how long does it take for the phonon to travel through a unit cell? Now, so you have this electron and you have this wake, and this wake persists for some time. Now the electron travels in this time, 1 over omega d, a distance which is roughly the Fermi velocity. We're dealing with the metal, so the electrons we're interested in move with the Fermi velocity multiplied by this time, so divided by this frequency. So while the wake persists, the electron has moved away by this distance, which is the Fermi velocity times the unit cell, the size of the unit cell divided by the sound velocity. Okay? In metals, the Fermi velocity is much bigger than the sound velocity. Well, in most semiconductors too. So this can be of the order of 10 to the 7 centimeters per second. This will be the order of 10 to the 4, 10 to the 5. So we have 2 orders of magnitude, likely, maybe even more. This may be even 10 to the 8 in some metals. So 2, 3 orders of magnitude difference. So the distance that the electrons travel is several unit cells. So the electrons can travel quite a distance while the wake persists. Now a second electron comes by. The second electron comes by and sees the wake, while the electrons, the other electrons, which in principle would repel, is farther away. And how farther away? Well, if it's farther away than the screening length, some Thomas Fermi screening length from the first electron, then the second electron coming by doesn't see the first electron because the charge of this guy is screened. So the net effect is that in metals in which the screening length is sufficiently short, the wake persists long enough, the density of the electrons is high, so that the probability that an electron comes by before the wake dies is high. What you have as a net effect is that an electrons will see a clump of positive charges along this trajectory of an electron which has long gone from the point of view of the first electron. So it will be attracted by the wake of this first electron. So the first electron and the second electron are coupled by the wake caused by the phonons. So it's an effect which depends on the presence of phonons, and if you want, it's an exchange of a phonon between electron number 1, which is now long gone, and electron number 2. So these two electrons may end up chasing each other, because now you can revert the situation. The second electron coming by also leaves a wake. This electron may go around, and we may see the wake of the first electron. So these two electrons may end up orbiting each other, chasing each other, and form a pair of electrons, a Coupling pairs. And this will have a binding energy delta. And as long as this is bigger than kT, there's nothing that can disrupt this situation. At large T, view this as a boat moving on a lake, leaving a wake, and a second boat comes by and tends to follow the wake of the first boat. If the lake is very calm, which means low temperature, which means there are no other ways, the wake left by the first boat will be extremely evident. And so the second boat will really try and follow the wake of the first boat. If the temperature is high, which in this analogy means the lake is stormy, or it's an ocean in storm, the wake of the first boat is completely washed out, literally, by the waves that are thermally excited. Also, you need high density. That's why you need metals, because at small density, the screening length may be so long that the Coulomb repulsion between electron number 1 and electron number 2 will actually prevent the formation of this pair. So, as I said, I was interested in two-dimensional materials, so there are lots of considerations in these slides that have to deal with 2D materials where things are very different, actually. So it's a change of the BCS theory. But in order to get superconductivity, you need low temperature, you need a calm lake, which means you need that very few other phonons being thermally excited, because these phonons may disrupt the wake of the first electron. And also, a big issue is a pure many-body effect that we'll have to consider in a moment, which is the Cooper instability. You actually have to confine everything inside a thin shell around the Fermi surface, which is not surprising. These are the only electrons that can do anything, as we know from, as we will see also in the expression for the electromobility, for example. Only stuff at the Fermi level matters, because electrons deep in the Fermi level cannot do much. They can go anywhere in energy and K-space because all states surrounding them are filled, and only when you have very large energies that can bring them outside the Fermi sea, above the Fermi sea, you can have something. So in relatively reasonable energy and wave vectors, only the Fermi surface matters. And it's a short-range interaction that we will see. So these are considerations that I said, actually, they make things different in 2D because in direct materials, it's always true that the Fermi velocity is bigger than the sound velocity. So you expect actually this process to occur more easily. The screening length does not depend on density in the electrostatic quantum limit in 2D. So this will also change something. And in two-dimensional material, in particular direct materials, they may become longer-range interaction rather than short-range. These are all considerations that make two-dimensional materials so interesting. As you know, actually, when was it? 2 years ago, they gave the Nobel Prize in Physics for essentially these topological and exotic properties of new material which have emerged recently: topological insulator, topological superconductivity, quantum spill-on effect, which is essentially the same thing. So there are new these new two-dimensional materials, and particularly the Dirac like graphene, that really have completely different behavior. Even if you stick to a BCS pictures, they look different because of many different situations, things that may happen. Nevertheless, let's go back to conventional superconductivity. I want to give you a flavor using conventional quantum mechanics of what happens and why you may have this Cooper instability. Cooper instability says that the degenerate, so high density electron gas, is unstable whenever you have a small attractive perturbation, attracted it to two electrons. It doesn't matter how small it is. As soon as you have a small attractive interaction between two electrons, the system collapses. into a new quantum state in which the single electron picture doesn't apply anymore. And this was actually shown by Cooper. And this led to the formation of Cooper pairs, and I think it was the beginning of the idea, I don't know, I'm not Bardeen, that Bardeen had to develop a full quantum mechanical theory of superconductivity. The difficulty of explaining superconductivity is, I will show it dealing actually with this Cooper instability, is that you cannot get there to the new quantum state following perturbation theory. And I think it's a sad situation that in the vast majority of the cases, let's say always, with a few exceptions, we don't know what else to do. We only have not to do how to do things perturbatively. Even in high energy physics and the theory of everything, the holographic principle in these things are extremely powerful because they can convert high energy to low energy. So you can do perturbation theory from both ends. But again, you rely on perturbation theory. The only examples that I know of theories beyond a perturbative approach are indeed BCS theory, the fractional quantum Hall effects with a McLaughlin state. If you want the standard model in physics for quantum chromodynamics, which had to be done with the Wilson lattice gauge models, so numerically with the big supercomputers that they did. Otherwise, we don't know what else to do if we have to abandon perturbation theory. So let's consider a system, two electrons. Now we're dealing with two isolated electrons, or one and two, and interact with some potential. Okay, this potential here. And this is the two-dimensional two-body Schrödinger equation, time-independent. Let's move to the center of mass coordinates as usual. So we define an effective mass mu. We see that we have a wave function that we can write in terms of the difference, the distance between the two electrons, and the average position, the center of mass position of the electrons, if you wish. Okay, so we can decouple the center of mass. These two electrons may be orbiting each other. This entire orbiting system translates in one direction. Let's move the translation of the center of mass over here with the from the orbital motion, and we get an effective equation, the effective center of mass, which is essentially what we do for the hydrogen atom, nothing different. We write the Schrödinger equation for the electron using the reduced mass. Of course, we replace the mass of the electron with the effective reduced mass here when we're dealing with the hydrogen atom because the nucleus weighs so much more than the electron. But for two electrons, this will be a different object, of course. And this E is just the energy of the bound state plus the translational energy, the way in which this two-body system moves in real space. Okay, nothing new here. Now, let's solve the problem. Let's Fourier transform everything, as usual, as I teach in one of the math classes that I teach to third year students. So let's introduce a wave function, which is the Fourier transform. So we go to Fourier space, psi OK. Let's introduce a quantum, a wave vector Q, which is the difference of the wave vector between the two electrons, and let's use epsilon K, the energy of the electron. So we can do a little bit of manipulation, rewriting this Schrödinger equation in this form. This is just having gone to Fourier transform, so now I have to deal with a Fourier transform of the potential multiplied by the wave function, which I can write it in this way by expressing the potential in terms of its Fourier components Q. And I ended up with this form for the Schrödinger equation. It says that in K space, I have this non-local term, this integral term, which gives me the energy of the state. And of course, there is this factor 2 epsilon K, which is the energy of a single electron. This should be a mu over here. Okay, let me define a new variable, a new wave function, if you want, which I call delta of K, which is this object. So if I replace inside here psi of K with this delta, okay, I have to divide by 2 epsilon K prime minus C. So solving this Schrödinger equation is fully equivalent to solving this one. It's convenient to rewrite it this way because I can find what are the properties of this potential which guarantee the existence of a bound state, so of a negative energy E, which gives me the two electrons can form a bound state. So let me assume a simple thing. Let me mimic this potential as an electron-phonon interaction by saying this potential is equal to some attractive potential V0 when the energy of the two states is less than the Debye energy, the phonon Debye energy, attractive. Otherwise it's zero, okay? I can do a little bit of algebra. I convert the integration over K over here to an integration of an energy, assuming sphericity, which I have. I assume that this delta is a constant now, and I find that this potential V0 has to satisfy this equation. And I want to see when I can have a negative energy E over here. And I find that the minimum potential for which this expression is verified, notice that I have the energy here and here inside the arctangent argument. It's a little deconvoluted, but you can deal with it. You can have a bound state, so an energy which is negative, as long as the potential has a minimum attractive value, which is given by this expression, which is actually very strong. So you must have a very strong potential. Again, this is the critical value that the attractive potential V0 has to have in order to have an infinitesimally small negative energy, bound energy, okay? So in general, you would say that, boy, I really need a very strong attractive interaction to make two electrons pair up. However, that's not true in general. Let's assume that now we started off by saying, let's consider two electrons. Okay, let's consider two electrons in an electron gas, which is a high density, which is degenerate. So now we do a little bit of a different story. We assume that this potential is attractive and negative, but only for states which are above the Fermi level, but within a Debye frequency from the Fermi level. So this represents the energy range in which the action can occur in a metal in which electrons can absorb, emit, do something, exchange phonons only from the Fermi level up, okay? So as long as the electrons have an energy which is within this shell of thickness h bar omega d, the Debye frequency, above the Fermi surface, then the electron is attractive, the interaction is attractive. Now the situation is different. Now we can approximate the density of states just with the density of state at the Fermi level, because everything happens at the Fermi level. This delta actually will be the wave function at the Fermi energy, and we find that we can integrate very simply this expression, having simplified this formula by assuming that delta is a constant and the density of states is the density of states at the Fermi level. So this square root of epsilon becomes epsilon f square root. And we can solve this expression, and we see that we can find that there is a bound state. These electrons actually couple into a bound state. So this energy, I've taken away the minus sign, but it's a binding energy, is given by twice the thickness. Okay, I should multiply by an h bar, twice the thickness of the shell that I have considered, times this factor, which is a dimensionless factor, which is the Fourier transform of this potential V0 times the density of states, which is actually a dimensionless factor. Notice that as V0 goes to 0, I get an essential singularity. So perturbation theory cannot reach this result. And this is the major feature of BCS theory, and this is why it's such a unique theory and required the intuition of Bardeen, driven probably by this idea of the Cooper instability. So the idea actually is that this thing is valid in any weak perturbation. If the perturbation is very weak, still you have a binding energy. So regardless of the strength of the attractive interaction, there's no minimum value for this V0. It can be as small as you wish, and this will give you, okay, the binding energy will go to 0. But for any V0, you can have a negative energy, which means that regardless of how weak this perturbation, this attractive perturbation is, the general electron gas is unstable. So it will collapse into a collection of Cooper pairs. So the system now will be a different system. We cannot view it as an electron gas constituted by single particles for which we can identify an energy. It's not a bunch of wave function of electrons that we have to consider. We need many-body theory now to describe this new collective state, which is described by wave function, an amplitude, a phase, which is actually what we use for quantum computing, for the Josephson junctions, to describe the system. Now, if we move to solids, there are some considerations. I don't know how deep I should go because now things get a little bit tricky and the technicalities are too much. So I will go briefly through them. I do not expect you to understand 100% of what I will say. I hope you understand at least 5%. It will not be part of an exam question or anything. What I said so far, yeah, I mean, the qualitative features may be interesting, but the details are a little tricky. The details are due to the fact that so the idea of superconductivity is the following. We have an electron coming in, it leaves a wake, and this wake is felt by another electron. So we can represent this effective electron-electron attractive interaction as an exchange of a phonon between the two electrons. This is as two dots. These two dots means that we have to go to second-order perturbation theory to represent the matrix element. The consequence of this will be more dramatic than perturbation theory suggests, as usual. But you see that the matrix element that expresses this interaction is this M is essentially our deformation potential. Okay, it's the usual strength of the electron-phonon interaction that we've seen already. And going to second-order perturbation theory, this is a standard second-order perturbation theory with some overall possible states K plus Q, and we have since it's dynamic, it's time-dependent, we have this frequency of the phonon moving around. The question is, hold on, look at this guy. This is positive. So it's a repulsive interaction. Not only, we're ignoring the Coulomb interaction, which is also repulsive. So where can we get an attractive interaction out of this? Well, the idea is that we can use second-order perturbation theory. We don't have to worry about higher orders. And this is because of a famous important theorem, which is called Migdal's theorem, that it says that you can ignore higher order terms. The details are a little tricky. The interesting thing historically is that, as I say here, Bardeen, Cooper, and Schaefer published the paper shortly after the Migdal's theorem. Actually, I should say before Migdal's theorem was published in English. But the Migdal's theorem appeared in the JAPT journal in Russian, in the original version in Russian, the year before. So did Bardeen, Cooper, and Schaefer know about Migdal's theorem? Because if we don't have it, then you have a problem, because here you have a singularity. You have a pole, a Q, when H bar omega Q is equal to the difference between these two energies. You have an issue. And instead, Migdal's theorem says, yeah, you don't have to worry about it. You can discard the poles. It contributes very little because the numerator is very small. So you really would have a principal part of an integral, if you remember, the Cauchy principal part. And it's very tiny because this varies very smoothly when the pole is. It's actually very big at large Q. And at large Q, actually, you can go and look only at electrons which are around the Fermi energy. If this is big at large Q, when you go at large Q, you see that there is a large region of K space where this energy can be very small. All the electrons which are populating a shell around the Fermi surface, around the Fermi sphere. And this can be for large Q, it can be quite a big volume. So this sum over the Q will end up being dominated by terms such that this term here is smaller than this guy. This guy grows with Q for acoustic phonons, right? You remember that we're approximating acoustic phonons here with some linear dispersion. So at large Q, this can be big. At zone edge, this can be 10, 20, 30, 40 millielectron volts. And this is a big energy shell over which you can, around the Fermi energy, at which this thing will be negative, because this will be almost zero. Ek and Ek plus Q are both around the Fermi shell, and this is 0, and then you're left with a minus sign in the denominator here. And so that was the idea. So flipping the sign, so now our interaction would be considered to have a plus sign, which is attractive, and minus sign, which is repulsive. You see that if we stick to electrons which are close to the Fermi energy, which is essentially what our heuristic argument at the beginning said, the electrons have to move fast for various reasons. One, the electron has to go far away so that it will be beyond the screening length in order that the second electron see its wake. And second, we must have electrons moving sufficiently fast so the flux of electrons is sufficiently high for a second electron to interact with the wake of the first electron. So this is always true in metals, and what we have is that we have an effective electron-phonon interaction which is attractive for those particular electrons. The other ones do not contribute because the denominator vanishes very quickly for all the other electrons. It gets very fast because this is of the order of, it goes like the Fermi velocity and this goes like the sound velocity. And so this, at large Q, this becomes negligible very quickly, except for those electrons which are around the Fermi energy, where this is becoming negative. So now, and this is what actually was a nice paper by Pines, says, well, so what we can do is we write this expression here, which is relatively simple. This is our deformation potential, whatever model we want to use. The Coulomb interaction is just this. We can use a simple Thomas Fermi model for screening here the Coulomb interaction. We integrate over the Fermi surface, which is what this square bracket, this bracket brace means, as long as this is, remember, I flipped the signs, okay? So as long as this is positive, which means the Coulomb repulsion is, of course, repulsive, but it's weaker than the electron-phonon interaction that we have, mediated by this process, then we will have the system to be a superconductor. You can formalize this thing if you want to have fun with these expressions. The idea is to take our Hamiltonian, which now is electron spin up, electron spin down. By the way, the interaction between the phonons is very strong when the wave functions of the two electrons close together, which means that the spins are antiparallel. So we have a spin singlet state for the pairs of electrons, which is preferred because the Coulomb repulsion is weaker, the electron-phonon interaction is stronger. So if you do that, you can consider only electron spin up, electron spin down. The xi's are their energies, the regular energies, whatever you have, around the Fermi sea. And then you have this effective Coulomb interaction between the electrons. This is just some overlap actor, which I was dealing with 2D materials, so for graphene this will matter somewhat. And then we have, you see, two electrons, one spin up and one spin down coming in. We destroy them, we kill them, and we generate two new electrons that have exchange of phonons. One electron gains momentum Q, one electron loses momentum Q, so we have exchange of phonons. The idea is, can I write this in this form as a diagonal way? The general way, the general procedure of taking a Hamiltonian this way, which is free particles, but they interact via some interaction, is to find a linear superposition of creation and annihilation operators of the two particles with this coefficient U and V that have to be determined, and see if you can write it in this form. And this corresponds to a full diagonalization of the Hamiltonian, in which these gamma now are creation and annihilation operators of these hybrids. Same thing in the plasmon and phonon that we considered before. These are now different objects. You take a pair of electrons and you form instead new quasi-particles for this particular, let's call it a condensate of Cooper pairs. Okay, you can do that actually. You can find what these are in terms of this parameter delta, which is very similar to the delta that we considered before for the Coulomb instability. And we find that if delta satisfies this equation, this is our overlap integral, this is the Coulomb Coulomb and phonon interaction between the electrons, this is normalization volume, and here we take just the expectation value of the number operators of these pairs, an electron spin up and electron spin down with opposite wave vectors. and the ground state energy is given by this expression. If we can find a solution for this equation, which ends up to be this way, it's an integral equation. The delta as a function of k is essentially an integral over the full interaction between the electrons. Ignore this term, and you see that there is the unknown itself over here. So it's an integral equation, and it depends on temperature. You can simplify it in a weak coupling limit, which means if you assume that delta is small, this E is given by the energy of the free particles plus this gap in this quadratic form, take the square root. So this is the expression. If you take delta small, then this integral is picked at the Fermi surface, not surprisingly, because we're assuming that everything happens at the Fermi surface. Then you can do, the integration by hand around the Fermi surface, and then you find that you can solve this equation, this integral equation, analytically, quasi-analytically, actually analytically, strictly, if you consider the Euler-Mascheroni's constant to be an analytic form, in which you can solve this equation in two limits, the limit in which the temperature goes to zero, and then you find the gap. What is the energy gap? Which is the binding energy, the energy that you gain when you make a transition for an electron gas to this collective, the conventional electron gas, to this collective superconductive mode, this collection of Cooper pairs. It's coherent, it's a condensate of Cooper pairs, okay? And you find what the gap will be. Notice that there is this exponential 1 over the density of states. For some reason in the superconductive literature, nu means the density of states of the Fermi energy. So I stick to this notation. And then this V effective, which is this average potential average over the Fermi sphere, integrated over the entire Fermi sphere. And remember that we had a similar expression for the Cooper instability. As long as this is a positive object, which means attractive in our convention, the system will collapse. There will be a gap, a non-zero gap. Only when this goes to zero, the gap goes to zero. Vice versa, if you set this is setting t equals 0, so the hyperbolic tangent goes to 1. If you set the delta goes to 0, this tells you which is the maximum temperature at which the gap, the critical temperature at which the gap disappears, becomes 0. And you find similar expression, this exponential. Again, it's this actually happens to be twice e to the gamma, where gamma is this constant. That you can find in Wikipedia for which how it is defined. So the important thing of the BCS theory was that it predicted something which had been observed experimentally, that there is a universal for all materials that obey BCS theory. The ratio between the KT and the gap is a constant. It's 1.13 divided by 2, which is 0.567. So this is a number which actually has been verified experimentally to a very good degree of accuracy, and this gives credibility, determine the success of the BCS theory because it was able to explain this feature. So what you can see is that essentially, if we look at this is the Fermi energy, this is some dispersion, some parabolic dispersion, all excitations and then electrons when you go above the Fermi wave vector. What you do is instead of having this point here, you open a gap. So your dispersion for the Dirac material will be different because now you open a gap at the Fermi surface. This means that once you have this condensate of Cooper pairs, in order for them to be excited in some excited states, you need to provide an excitation via perturbation, a scattering process or something, which is bigger than this gap. So if this gap is bigger than KT, thermal excitation do not destroy the coherence of this mode, and these are just pairs that keep moving, and so they carry charge without any scattering being possible. Only when you increase the temperature or you give the system an energy which is bigger than the gap, you can destroy this coherence. And that explains the superconducting behavior. Where do we stand now? BCS, they're labeled somewhere. Oh, here it is. These are the BCS theory. You see that we go from few degrees. Actually, there are some magnesium boride, for example, that can have transition temperatures which approach 40 degrees. Notice the break in the temperature. Okay, I jump from 50 from 49 to 100 here. Okay, so these are the conventional BCS materials. From 1986 on, there have been heavy other materials, mainly the cuprites. These are the first materials that were discovered in 1986 that had temperatures in the 30s, so not in great competition with these guys. But then eventually, shortly afterwards, there was a big jump towards 150. Somewhere the highest record that I saw in this chart, it seems to be bigger than 150. Looking in detail, I found that at room pressure, the record is 133 Kelvin, whatever. Here actually is at 30 gigapascal. This seems to be at room pressure, seems to be higher than 133, whatever it is. This is through 2015. This is a chart that I found in Wikipedia, but the highest temperature that we have now in 2019 was this material at 155 gigapascal, lanthanum hydride of some sort. But later last year, there were reports of the first above room temperature. I don't know what you consider room temperature. This is 15 degrees, right, Celsius. So it's a colder room, but it's you need a sweater. But it's still room temperature. I couldn't find out exactly what material it is. It is defined as a carbonaceous sulfur hydride. So it's some hydrogen thing, because actually hydrogen was supposed to be a superconductor at high temperature at very high pressure when it becomes a liquid. So this is where we stand. How is it used? This is, for example, a picture that I found of an IBM super quantum computing chip made up with this object, which is essentially Josephson junction. They're transmission line shunted plasma oscillations, but these plasma oscillations oscillate through Josephson junctions, which are superconducting junctions. And I'll tell you in a minute how they're used vaguely. Now we have up to 20 qubits. I'm not sure that that's the record, actually. I think that there are arrays of trapped cold ions, which have more than 20 qubits. So there are arrays of, I don't know, something like 8 by 8 qubits. I'm not sure. All I know about quantum computing is a few talks, a few articles I read without understanding, and Wikipedia, the full knowledge of all, the full place of where you find the human knowledge. So what is quantum computing? Why do Josephson junction and superconductors are useful? So the basic idea, as far as I understand it, of quantum computing is that in a classical computer, if you have two inputs, you have 2 bits. These inputs can be 0, 1, up or down, whatever it is, plus or minus, as we call it here. And we process each input separately. So you input plus and you see what comes out, you input minus, you see what comes out. Quantum computing, for the same case of 2 inputs instead, the 2 inputs will be considered to be entangled, which means that the 2 inputs are described by a single wave function, coherent, which is a linear superposition of all the possible states that you might have. So the entangled states would be plus, 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 minus, minus, plus, which are different because the 2 inputs are considered to be distinguishable, and minus, minus. So these are 4 different states rather than 2, and you can process them simultaneously. And then you, of course, at the end, when you make the measurement, you see the results of your measurement, you collapse into one of the possible states, but this gives you information anyway about what was the process done on the various inputs. So if you go to many inputs, you see that you have a tremendous advantage in how many possible combinations of entangled states you can have. And you can also have multiple states. Here we're considering just an up and down or a 0-1 state. You can have an entire, what's called a block sphere, the various phases that connect the various possible states of, the phases of the coefficients that constitute a superposition of the various states of the system, eigenstates. I don't know much about possible logic computing and algorithm implementations that are possible, including reversible quantum computing, and the applications So far, I think they've mainly been used for prime number factorization. I'm not sure how many digits they could factorize, but that's the typical intent use. Search algorithm, it's another intended applications. Of course, since you rely on quantum processing of this linear superposition of states, if you want to model theoretically quantum systems, you can actually do it, account for the quantum mechanics of the system automatically, the way you do the processing. Quantum annealing, machine learning, lots of ideas. And the possible implementation are of qubits. So what is one of these inputs? What is this one of the logic gates, if you want? As the record that I think you may verify, I'm not sure. I heard a talk last year, well, before COVID, about trapped cold ions, and it was impressive how many cold ions they can put in an array and address optically. So the idea is that each cold ion can be either excited or in its ground state, and you can actually form entangled states of these systems by using entangled phonon states to excite them or de-excite them. In principle, you can also extend it to multiple excited states, and when you do that, essentially this constitutes an input, and you can process them simultaneously in these arrays. In principle, you can do the same optically. Photons, of course, can be put in a linear superposition, interference, we call it. The usual problem with these things, this is the low temperature, is the magnetic field you need to apply. The drawback of photons is the usual drawback of quantum computing. Photons are big, they are not as small as electrons, so typically they are cumbersome in size. Spins, entangled spin up and spin down states, these would be both nuclear spins and electronic spins, and you can use spintronics in some way extended to quantum computing. Quantum dots, these are, you can have entangled charge or neutral states, you can have spin states, you can have excited states if you want, so multiple charge states, you can put multiple electrons in a quantum dot. The main problem of these, as well as spintronics in semiconductors, is the reproducibility, the fidelity. All of the dots should be the same to have a real entangled state, and that's an issue. There are some criteria which actually were formulated by Dave DiVincenzo years ago that define what a qubit should be, and sometimes you have issues. Josephson junction, which is what we're dealing with here, superconductivity, you can use many ways. You can use this collective condensate or Cooper pairs, which again is described by wave function, which has a phase and an amplitude. And you can use the phase to have some coherent superposition of various states. You can use the amplitude, which amounts to the charge that you have. You can also use flux, particularly the flux in superconducting condensate through a magnetic loop, for example, is quantized. And that's an idea where you can define states of these magnetic quantities, for example. And now there are, of course, with the advent of topological systems, lots of other ideas about entangled excitations for gap topological insulators. The main problem in all of these is how do you preserve coherence. So for Josephson junctions, it would be good, except for the fact that you need low temperature, and this can be an issue. I'm not sure what temperature they've used these things. That's why the idea of using two-dimensional materials which have superconductive properties at relatively high temperatures would be interesting. I had an idea with the coupling with the flexural modes in graphene, which I told you about the Merny-Wagner theorem. I was expecting much more because the electron-phonon interaction actually diverges at low wavelengths. So great, if it diverges, we should have temperature superconducting at superconductivity, very high temperature. Unfortunately, it doesn't work out that way because of density of states and scaling effects. So it's in the 5 to 10 degrees, so Kelvin, not much. So I think for today, I would stop here unless I have questions. Remember, this thing is something that, as I said, I know approximately nothing. I'd probably say nothing wouldn't be too far off the truth. So I'll do my best to answer questions if you have them. And I hope that you found this brief discussion about superconductivity, particularly its heuristic origin, the role played by the electron-phonon interaction in setting up superconductivity, which is kind of surprising. How should electrons interact, be attracted by exchanging a phonon? But that's actually the benefit, the genius of the Verdin-Cooper-Schrieffer theory. So I'll stop here unless I have any question. No question, no comments. You're all happy? All right, then I will post the slides. Next week, we will go into other type of interactions, scattering with ionized impurities and electron-electron. Electron-electron interaction, we can talk forever, so I will see how to behave, and radiative recombination, just a brief reminder. And then we'll go finally into transport. And for that, we will go into formulating a little bit the density matrix equation of motion for the density matrix. So we'll have to go back a little bit into what is the density matrix, what is the Liouville-von Neumann equation of motion for the density matrix, and how to go and describe transport. I have my own personal perspective on quantum transport and how to go from the von Neumann-Liouville equation of motion to the Boltzmann transport equation. Then we'll go to the Boltzmann transport equation. And I think we have 5 more group of lectures, 5 or 6. So we don't have much time to go into too many details, but I'll do my best. Okay, then have a good weekend. And I'll see you next week then.
Thank you. Thank you, Max.
Bye-bye.
Bye, Massimo. Ciao.
Ciao, ciao.
Thank you. Bye-bye.
Bye-bye.
Buon fine settimana.
Anche a te. Ciao, ciao.
Ciao.